Hi, thank you, Carol, for that short introduction. And I want to thank Cyprien and yourself for inviting me for this talk. So my name is Caspar van Lissa. I'm an associate professor of social data science at Tilburg University in the Netherlands and chair of the open science community at that university. What I'll be talking about today is an obsession that I've had for some years. And it's this question of how to deal with heterogeneity and meta-analysis. This is closely tied to my own story of becoming a methodologist, because I started out as an applied researcher in adolescent development. And at some point during my postdoc, I was asked to do a meta-analysis by my supervisor. I thought, okay, so I collected these data and coded all these studies. And then I realized they're really different from each other. And if I read the methodological literature, meta-analysis requires that your studies are on the same topic, with the same kind of scales, with the same kind of effect sizes. What do I do about this? And there wasn't really a solution. And digging into potential solutions gave rise to the research that I'm presenting today. So I'm going to open up my slides and share them with you. Do you see them now?
Yes.
Yeah, okay, very good. And I'll try to make them big. So I'm talking about using insights from machine learning on how to deal with heterogeneity in meta-analysis. And that kind of gives away the answer to the question of how to deal with heterogeneity. But here's a brief introduction. So when we collect meta-analytic data using systematic review methods, which I understand have been addressed at the previous of these talks, we have to make some assumptions about heterogeneity. One situation we can find ourselves in is where the studies are too different, and we can conclude they're so different that we won't meta-analyze them. And in this case, for example, we might formalize a decision criteria to in or exclude studies that we consider to be too different to be quantitatively summarized together. Another case we might find ourselves in is when studies are similar, but they are not identical. And then we can make assumptions. For example, an assumption that effect sizes out there in the population follow, say, a normal distribution, and then we can estimate that distribution and meta-analyze the studies using a random effects meta-analysis. But we can also say, well, I know my studies are different, and I can pinpoint exactly in which ways they're different, but I'm not going to use it as an exclusion criterion. I'm going to use it as a moderator. So I'm going to code those differences as an extra column in my data set. For every effect size, I have a value on this moderator, and then I will control for them using, for example, meta-regression. So if we dig a little deeper, we find that there are some superstitions about meta-analysis. A lot of people speak of meta-analysis as the gold standard of evidence. There's this nice triangle inspired by Maslow's hierarchy of needs, where people place meta-analysis at the very top, and it's treated with a lot of reference. And what I've seen is, reading between the lines in a lot of applied meta-analyses, is there are these superstitions that it's somehow immune to small sample problems. People very often, for example, just cite like the total N across all studies, ignoring the fact that they have only maybe 10 studies in their meta-analysis, and that the unit of analysis is the study. So you, in fact, are dealing with a sample of 10, not a sample of 300,000 or however many it may be. So when we are doing meta-analysis, our unit of analysis is the study or the effect size, and often we have a small sample, but there are also often many moderators, many differences between studies that sometimes people measure, but very often they don't analyze, or sometimes they don't even code them. So just to recap, I'm sure everybody in the call right now is quite aware of this, but it's a good foundation for the rest of my talk. There are a few classic ways to deal with heterogeneity. The first case is when you can assume that there's no heterogeneity. For example, when your sample consists of identical or close replications, then you can assume that there is a fixed effect that all these studies share. And you can do a fixed effect meta-analysis, assuming that all studies tap into one true effect size and that any observed differences between the effect sizes are due to sampling error. In this context, you can think of meta-analysis as a weighted mean of the study effect sizes, where studies with bigger samples have more influence. There's also random effects meta-analysis, which I already alluded to. In the case that your studies are similar, but they're not identical replications, you could assume that true effect sizes follow a normal distribution. You can then estimate the parameters of that distribution. And now we assume that differences between observed effect sizes are due to a combination of sampling error, just as before, and the variance of this normal distribution of effect sizes in the population. What happens then is that weights allocated to studies are based on a combination of the precision of the effect size and the between studies heterogeneity. And in practice, that means that study weights become more equal the larger the between study differences are. So if the variance parameter of this normal distribution of true effect sizes is very large, then you can assume that each study is giving you some unique information about a different part of that distribution, so they should all be weighted more equally. But there are other sources of heterogeneity. In practice, particularly in the social sciences, which is where I work, but perhaps also in your field, I'm no expert, you can share it later in the discussion, there are often differences in terms of the sampling plan, in terms of operationalizations of variables, in terms of different methods, all of which can introduce heterogeneity in the effect sizes. So in practice, the same research questions are often studied in different ways, in different labs, in different places around the world. And all of those differences can cause a difference in effect sizes. So one thing that people do to deal with this is they use meta-regression, and then they assume that the true effect size is a function of different moderators, which can be coded and included as predictors. And whatever is left over in terms of unexplained variance can be attributed to either a residual fixed effect or random effect, but usually it's a random effect. Now, meta-regression, like any other regression-based technique, requires a lot of cases per parameter. You need a data set that is longer than it is wide, simply put. But when the number of effect sizes or studies is relatively small, we often end up in a situation where meta-regression lacks the power to test more than a few moderators. So in machine learning, a little preview, this is called the curse of dimensionality, and it's one of the key challenges that that field deals with. Let me illustrate. So imagine that we have a data set with 7 studies, and we're going to describe those data with a model. In this case, it's just a simple model with only one parameter, which is the intercept. So we see here 7 data points and a red line that represents the intercept or the mean of those 7 data points. And the mean explains 0% of the variance in those data. If we then add a linear effect of one predictor, we get a diagonal line, and it explains 8% of the variance. And we see that there are quite large discrepancies between the data points and that line. And we could theoretically keep adding parameters to this model to improve our fit to the data. So what happens, for example, if we add a second order polynomial? Well, now we explain 38% of the variance, and we see that the points are quite a bit closer to the line that represents the model. And we could theoretically keep adding parameters here. We could add the third order polynomial and the fourth and keep going. For example, here are the third and fourth, and now we explain 68% of the variance. But we also see an interesting phenomenon happening. We see that the red line, which represents our data model, starts curving quite extremely between the data points in order to get closer to those data. And this is a phenomenon called overfitting. Because if we go, for example, here to this part of the curve, we see that our model is making quite extreme jumps, but there are no data there to inform those jumps. Those jumps are purely coerced by the fact that it's trying to fit those few sparse other data points. And if we keep adding even more parameters here, such as the sixth order polynomial, now we explain 100% of the variance. The model hits every point exactly. It makes bizarre jumps between the data, so we can no longer trust this model. This is fully overfit, and in fact, we have here a model with 7 parameters to describe 7 data points, so the model is just a re-expression of the data itself. This gets quite close to some meta-analytic data sets that I've seen in practice, because as a statistical consultant, I speak with a lot of people who try to do meta-analyses, And sometimes they have really small data sets and quite a lot of moderators. So they could end up with a similar problem of overfitting. So what we have to do in this case is to determine in some way which study characteristics are relevant and influence the effect size. How do we go about that? Well, one way is to use theory to select relevant moderators a priori. But the problem is that we often lack theory to whittle down the list of between study level moderators. Because if we use, for example, theory about the units of analyses that our studies are about, then we commit the ecological fallacy by assuming that an effect that happens amongst our participants also influences differences between our studies. So if you think about it this way, there are actually very few theories about study level differences. One example that is a theory about study level differences is the decline effect. It's a finding pointed out by Schooler that effect sizes in any field tend to diminish as chronological time progresses. And it's attributed to regression to the mean. So the idea is that any phenomenon picks up steam in science if a few initial strong effect sizes draw attention to it. But then as other researchers pick up the topic, thanks to regression to the mean, they find smaller effect sizes than those few initial findings. So based on this decline effect, we could hypothesize, for example, that year of publication is a relevant moderator of effect size. And that prediction is valid even if year is orthogonal to the outcome of interest within the individual studies, because it's a between study level moderator. But there are not many other theories at the study level that I could find. So an alternative, instead of using theory, is to use statistical solutions. So can't we just use bivariate null hypothesis significance test? We have 8 moderators, so we do 8 random effects meta regressions, and we see which one is significant. Well, that's a problem for several reasons. First of all, because p-values are not designed for model selection, but for performing inference on a priori hypotheses. Second of all, we end up with a multiple testing problem. Of course, we could control for that. A third problem is that we end up overfitting the data by reanalyzing the same sample over and over, cherry picking significant results, and then putting those predictors together in another model. And the final limitation is that for each of these analyses, the p-value depends on what other variables are there in the model. So the way that you approach this variable selection process determines what the final model is that you end up with. Could we use information criteria? Well, it does penalize for model complexity, so that addresses the multiple testing problem. But if you use information criteria, you have to explicitly define the entire search space of all possible models that you want to compare. And a third way that I could think of is variable selection. And that's a key issue in the machine learning literature. So that's the approach that I took. There was an initial application of machine learning to meta-analysis when I started this work. It was by Elise Dusseldorp and her colleagues. And they used classification trees to explore which combinations of study characteristics together predict effect size. So the dependent variable here is effect size, and the independent variables are the moderators, the study characteristics. I can explain this technique very briefly. So imagine that we have 2 moderators in our data set, 2 between study differences. And we just want to know whether those 2 moderators determine whether the effect size is big or small. So I've dichotomized effect size for convenience. We can represent those data the way I did in the picture here. So we see that red dots are studies with large effect sizes and blue dots are studies with small effect sizes. And we see that there's a pocket of studies with large effect sizes right here. So using a classification tree, we could split up this sample in such a way that we capture all of the studies with large effect sizes. And that would work as follows. First, we make a decision rule where we split the sample on the first study characteristic, x1, and we split it depending on whether a particular effect size has a value on x1 bigger or smaller than 0.5. And what that does is it assigns all of the blue effect sizes here to one group. And it assigns all of the red effect sizes and a few blue ones to another group. we could then further split this group using a second decision rule. If the study has a value on the second study characteristic larger than 0.3, it's assigned to one group. And if it has a smaller value, it's assigned to the other group. Now we also got a perfectly homogeneous cluster of blue studies here. And we've got a little bit of heterogeneity here left. And if we split that one more time using a decision rule on X1 again, we've perfectly explained between study differences in effect sizes that are either big or small using several decision rules. The good thing about tree models is that they easily handle situations where there are many predictors relative to observations. They just ignore irrelevant predictors and only use the relevant ones to partialize the sample the way I just illustrated. Another nice thing about trees is that they inherently capture interactions and nonlinear effects of moderators by forming sequential splits. For example, if there's a nonlinear effect, they can split multiple times on different points on the same predictor variable. And both of these things are likely the case when performing meta-analysis in a heterogeneous body of literature. Effects aren't likely to be linear. But there are also limitations. A single tree model is very prone to overfitting the data. They also suffer from what is called the illusion of interpretability. It looks so beautiful, this kind of decision flow chart. It's easy to read, easy to interpret, but it's only a description of how the model came to its decisions. It's not a good description of the underlying data generating process. And the reason for that is that tree models are often very unstable. So right now I split on X1, for example, but if X1 is strongly correlated with X3, I could have just as easily taken X3 there. Or maybe I could have split at just a slightly different point, and then all of the other downstream decisions would be affected. So tree-based models tend to be very unstable, and because of that, you have to be careful about interpreting them. And a specific limitation of the meta-card method is that it uses this tree-based model and then follows it up with a multi-group meta-regression. And the reason that's a problem is because the tree-based model is non-parametric. It has no incentive to homogenize variance in the different groups resulting from the splits. But the multi-group meta-regression assumes homoscedastic, normally distributed residuals in all those groups. So it's a poor match with the tree-based splitting method. So what I first tried to establish is an alternative approach to a single tree. And that's the metaforest technique. So metaforest is based on random forests, which tries to solve some of those aforementioned limitations of a single tree. And the way it does this is by drawing many bootstrap samples of the original data, let's say 1,000. And then for each bootstrap sample, it grows a tree in the same way that I just explained. And to make sure that every tree learns something unique from the data, whenever it's about to make a split, it can only look at a random subsection of the moderators. And then it has to pick the best moderator out of that random subset. So every tree is going to look a little bit different. Now, once we have our 1,000 trees fully grown, we can average the predictions that are made across all of those trees. And what that will accomplish is that it averages out any noise, idiosyncratic noise in the data that has been fitted, and it gives you more reliable predictions on the aggregate. So I changed this algorithm slightly by making the bootstrapping step a weighted bootstrap. And the weights are determined based on fixed effects weights from meta-analysis, or random effects weights, or uniform weights. And then you can use a process called cross-validation to determine which of those different weighting processes gives you the best results. So you can think of those different weights as being on a sort of continuum. On the one end is the fixed effects weight, which says every study is measuring the same effect. So big studies should be more informative. And on the other end of the extreme is a uniform weight, which says, well, every study gives me completely unique information, so you shouldn't weight it at all. And random effects are kind of in the middle in a data-driven way. So what typically ends up happening is that just like in classic meta-analysis, more precise studies will be more influential on the random forest. So this method has a few advantages. It's more robust to overfitting than individual trees because noise captured by those trees averages out across samples. Random forests also make better predictions than individual trees because a single tree predicts a constant value for every group. But if you average the predictions of many trees, you can fit really smooth curves. So if you have, for example, a nonlinear effect, that will be better represented by a forest than by one single tree. So if you use this method, what are the outcomes that you would report about in a paper? Well, the first outcome that I think is relevant is the predictive explained variance. This is similar to the explained variance you would report for a standard regression model, but the difference is that it is an estimate of how well this model generalizes to new data. So that's nice to know. So instead of saying, well, in the data that I already have, I can explain 38%. Instead of that, you say, well, I predict that I can explain 38% of the variance in new data. Another outcome that's relevant are variable importance metrics, and those tell you which moderators most strongly predict the effect size. This is the variable selection step that makes it useful for meta-regression with many moderators. And another outcome that I think is relevant are partial dependence plots. Those show you the marginal shape of the relationship with each moderator with the effect size, averaging out all other moderators. And finally, these models can give you predictions of expected effect size, which is really useful for planning future studies or for power analysis, for example. So is this method any good? Well, we did simulation studies to check, and we examined the method's predictive performance, its power to detect a true effect, and its ability to distinguish irrelevant from relevant moderators. And all of those analyses can be found at the link referenced here on the slides. I will focus briefly on one simulation study here. So we manipulated a few design factors in this study. We manipulated the number of effect sizes, so the number of studies being meta-analyzed, and we selected values of 20, 40, 80, and 120. We also manipulated the average within study sample size, 40, 80, and 160. We manipulated the number of irrelevant moderators, so distractors, if you will, and we manipulated the true population effect size of a relevant moderator. We manipulated the residual heterogeneity, and we used 5 different models to simulate data. So the most straightforward one is a main effect of one moderator, but we also looked at interaction effects and nonlinear effects. And to determine practical guidelines for the usage of this method, we were looking at basically a standard power analysis situation. Under what conditions does this new method achieve a positive explained variance at least 80% of the time? So under what conditions does it detect an effect at least 80% of the time? And this is a plot that is kind of hard to read, so I will summarize it with one sentence. It usually does within the parameters of all of those design factors that I just described, except when the effect size is the smallest that we manipulated it to be, so 0.2, and the heterogeneity is the biggest that we manipulated it to be. Under all other conditions that we simulated, it achieved this power greater than 0.80. And in this figure, we also show that in a lot of cases where meta-cart does not achieve that kind of power, meta-forest does. But I now think that that finding is less relevant. So summarizing the results, we find that meta-forest had sufficient power in most conditions, even for as few as 20 effect sizes, except when the effect size was small and the residual heterogeneity was high. And we also find that power was most affected by the true effect size and the residual heterogeneity, followed by the true underlying model. And of course, the true underlying model is a combination of the true effect size and residual heterogeneity. So those 3 things hang together. So before I go to another part of the presentation, if you want to use this, you can just use a standard meta-analytic dataset with several moderators. And the software to do these analyses is available on the central R package repository CRAN. And you can get it on your computer if you use R by running this command. And then you can see the help file by running !:metaforest. And if you're not an R user, there is a visual interface that is run on a website. So I will skip this for a second and I will go to the second model that I want to describe, because I always thought that we could do better than MetaForest, and I'll explain why in a second. And that's why I developed this second approach, which is penalized meta-analysis, or PMA. So why another technique? Well, I published a lot of applied papers where we used the MetaForest technique, and I found it was hard to explain to reviewers. And also, we always had to include a lot of explanation about the random forest technique when explaining it to the readers. So I just realized that the scientific community tends to be more familiar with linear models, and it would be really nice if we had a linear model that could also perform moderator selection. And the second thing is that I have concern that despite the simulation studies showing good performance with small samples, the results are often unstable when we have small real data sets. So I felt like I wanted a better tool in my arsenal for small meta-analytic samples. And that became PMA. So how does PMA work? Well, this formula here represents the standard meta-regression model. And we are modeling the observed individual effect sizes as a function of some intercept, plus the effect of multiple moderators, plus the standard deviation of the random effect, plus residual unexplained heterogeneity. And this model is typically estimated using restricted maximum likelihood, which minimizes the residual sum of squares after fitting this model. So any kind of maximum likelihood based model has low bias, and the estimated coefficients will be really close to the true population value. But low bias always comes at the cost of high variance, which means that your estimates are completely dependent on the data in your sample. So from one sample to the next, there will be a lot of variance of the estimates. This bias and variance is traded off. And in machine learning, what's often done is that people choose to intentionally increase bias so that the variance of their estimates will reduce. And what this accomplishes is that your estimates will generalize better to new data sets. It's also, in a way, you could say that your model becomes less excited by data. And because of that, it doesn't tend to capture noise as readily. And this is very advantageous when you have a small data set, because small data sets tend to have quite a lot of noise. So the technique that we implemented here is regularization, which decreases variance by increasing the bias. So we used at the beginning the L1 or lasso penalization, and it minimizes the residual sum of squares, just like standard regression does, but it penalizes the size of coefficients by adding the sum of the absolute coefficients to the quantity to be minimized. So here we see this simple formula. We see the residual sum of squares from the previous page plus some kind of weight times a sum across the absolute regression coefficients of our moderators. So now we give the optimizer an incentive to keep some of the regression coefficients small. It's been known for a long time that the frequentist implementation of this lasso penalization has an analog in a Bayesian approach to statistics. Specifically, in Bayesian terms, the lasso penalty corresponds to a double exponential prior, visualized in the picture over here. And the prior tells us what are likely values for the parameter to have. And what we see is that there's a lot of probability mass assigned to 0. So we're basically telling our model, go ahead and estimate the parameters, but I think they're very likely to be close to 0. So also here, it has an incentive to keep the regression coefficients small. Bayesian analysis combines this prior expectation with the information contained in the data. And it has several advantages, which is why I'm introducing it here. The first advantage is that unlike frequentist lasso penalized meta-regression, this can be implemented in readily available existing software. Secondly, we don't just have this lasso penalty if we use the Bayesian framework, we can use any kind of regularizing prior. And there are priors that are a lot better at regularizing than the lasso. For example, the horseshoe prior also has a lot of probability mass around 0, but it has heavier tails, which means that if an effect size manages to escape the 0, it will be less biased than it will be with the lasso prior. So what we did is we implemented different kinds of penalized Bayesian meta-regression using a backend in Stan, and we developed a new package called PIMA, which implements this method. The nice thing about PIMA is that all of the code is compiled, and this has two advantages. One, it is really easy for users to install because you don't need to be able to compile your own models. And the second thing is that it's a huge time saver because compiling a model takes a lot of time. So is this method any good? Well, we validated it again using simulation studies. And in these studies, we compared three methods. We compared lasso penalized and horseshoe penalized Bayesian meta-regression to the industry standard restricted maximum likelihood meta-regression using metaphor. I see that Wolfgang Wichtbauer is also in the call today, so it's very nice that you're here. So we compared it to metaphor, and the simulation conditions, which I think were dropped here, but they are similar to in the previous slide. And the performance indicators that we looked at were once again predictive R-square in a new sample, the ability to recover the true value of population parameters, and sensitivity to detect a true population effect and specificity to reject false, non-existent population effects. And all the code is available at this link. Here are the simulation conditions. So again, they're similar to before. So what we found is that within each iteration of the simulations, Bayesian regularized meta-regression with the horseshoe prior had the highest predictive performance, 50% of all replications of our simulations, followed by the metaphor approach and followed by the lasso approach. What we also found is that the predictive R-square was higher for the horseshoe Bayesian regularized models in the presence of a true population effect. And we found that metaphor tended to have a more negative predictive explained variance if the population effect was 0. So that information you can see here, and briefly summarized, what we see is that if there was a true effect, the two different Bayesian approaches tended to have a higher predictive R-square. And if there was no true effect, metaphor tended to have quite a negative predictive R-squared. And that's a sign of overfitting. So that's a sign that metaphor found something in noisy data, but that something did not exist in the population. And because of that, when we try to predict a new sample, we get a negative explained variance. We also found that the sensitivity to detect true effects was highest for metaphor. So that's a major point for metaphor, but closely followed by our horseshoe prior and then lasso. And predictably, we found that specificity was higher for both of the regularized algorithms. So very simply put, if your goal is to find true effects, then use metaphor. If your goal is to eliminate irrelevant moderators, then use horseshoe penalized meta-regression. And now comes a really nice thing. The overall balance between sensitivity and specificity was approximately the same for metaphor and for our penalized approach. So that means that you can really pick which one of these two methods you want to use depending on your goal. Do you want to find a true effect at all costs, or do you want to eliminate as many irrelevant moderators as possible? If it's the former, then use metaphor. If it's the latter, use Bayesian regularization. So finally, I will address bias because I mentioned that this method increases bias to reduce variance. So predictably, For the regression coefficients, the horseshoe prior had the greatest bias, followed by lasso, and metaphor has almost no bias, which is what we expect. But do note that even metaphor had a little bit of bias, interestingly. We also find that the horseshoe had the lowest variance, again, predictably, because we're trading these two off. But if we look at the residual heterogeneity, tau square, we see something very interesting. There we see that the horseshoe had the lowest bias. And we were not trying to reduce bias in somehow for the residual heterogeneity, but surprisingly, we see that our penalized method performs quite well here at estimating the residual heterogeneity. Okay, so just to sum up, some advantages of Bayesian regularized meta-analysis over industry standard metaphor is that Bayesian regularized meta-analysis has better predictive performance, especially when there is no true population effect. Results from the regularized approach are less overfitted, and that makes them suitable as a small sample solution. I also want to mention here that for quite a few of our simulation iterations with small sample sizes, RMA did not converge, and we tried all of the tricks to increase convergence that were mentioned on the Metaphor website. We can also conclude that the Bayesian regularization is better at rejecting irrelevant moderators from a large set of potential candidates than Metaphor. And we see that the overall variable selection accuracy remains equivalent to Metaphor. So you can really set your goal and pick a suitable method based on that. Estimated regression coefficients are biased towards zero, but that is by design. Interestingly, the residual heterogeneity did not show evidence of bias. And a nice thing of this method is that it's an extension of the linear model, which is familiar to most researchers, and you can incorporate predictors of any measurement level, interaction terms, nonlinear effects. So it's quite flexible. So implementations, and after that, I will go to questions. Like I said, you can get metaphors just from CRAN. Here's an example of an analysis. I also wanted to illustrate that it's suitable for multi-level data, so you can cluster if you have multiple effect sizes from one study. You can look at model convergence. So you want to see this line straightening out. That will tell you that your model has converged. You can get these partial dependence plots that I described earlier. So for example, here we see kind of a step function with two steps for the effect of age. You can get variable importance metrics. So this analysis shows you that only intervention and age are relevant moderators. The other moderators are negative in terms of variable importance, so they are not important. And you can even probe interactions using a heat map. There's a web interface that will give you access to all of this for people who don't use R. And if you want to use PIMA or Bayesian regularized meta-analysis instead, you can also get it from the CRAN repository. It also has extensive help, and there's a preprint currently in Revise and Resubmit. The nice thing about PIMA is that it's compatible with RSTAN and other related packages. So all of the plotting and diagnostic functions that already exist for Bayesian models are directly applicable to your Bayesian meta-analysis with PIMA. And here's an example of what an analysis looks like using an example from the manual, and you just get basically a regression table that should be familiar to most people. And that's really all that I wanted to tell you. So I hope there are some questions and that we have a bit of discussion going. Thank you for your attention.
Great, thank you so much. That was so interesting, actually. So if we'll actually just take questions too by people raising their hands, or you could just type something in the chat. Wolfgang, would you like to ask your question in person?
Okay.
Okay. So I'll
I've been
just
there.
I'm sorry to hear that, actually. That's too bad. So I'll just read out the questions for our recording. So did you also try bagging and boosting for the tree-based approach?
Yeah, so that's a very nice question. First of all, thank you for being here despite being sick, and feel better soon. I think that the method that I developed with metaphors can be easily extended to that situation. And a reason that I haven't developed it is because I'm trying to provide methods that help the researchers that I collaborate with resolve practical problems that they have. And I just experienced after I developed metaphors that most of them had samples that were just too small to get robust results. So I thought that is the most urgent problem that I have to solve now, not eking out some imaginary last bit of explainable variance by using perhaps superior implementations of tree-based models. Yeah, so it was really a matter of where I allocate my priorities. And I always thought that regularized linear regression would be the best solution for most of the people that I work with. But you can do it. It's certainly possible.
Great, thank you. So maybe while we're waiting for some more questions, we can start our poll, our last poll. And also, I was just wondering, I know these are fairly new methods, but have any other researchers used your methods and published with them?
Yeah, quite a lot. I forgot how many. I think there's like 60 citations in total at this point. And I'm not keeping track of all of this, but two papers that I do keep track of are Nature Geoscience and a Nature Climate Change publication, which have gathered quite a lot of attention. And that's, of course, really nice to see. And I also have several papers in the pipeline that use the Bayesian regularized linear model. And I'm just really happy with how useful that's proving to be for working with applied researchers, because it looks like regression, so they can interpret it easily, but it does solve the problem of the small sample sizes.
Great. So we have another question from Diego, who asks, overall, would you then recommend the PIMA approach over the random trees approach?
Yeah, thank you, Diego. It's a good question. Yes, I would, but maybe that's just because PIMA is the new shiny thing for me. But what you could also do is compare both approaches. So in machine learning, it's very common to set up an outer cross-validation loop where multiple models are compared, and you go into it model agnostic, and you just pick whichever one has the best predictive performance. You could do that here too. And an alternative approach is to just look at the specific use case. If you have a large sample and you expect complex interactions between moderators, then random forest is probably better. And if you have a very small sample and you just want to have a model that converges, then PIMA is probably better. Because that, I should probably emphasize that, so PIMA does not intrinsically accommodate interactions and nonlinear effects, right? So the nice thing about random forest is if you feed it a lot of data, it will figure out if there are nonlinear effects or interactions. And with PIMA, you have to compute those terms yourself and add them to the model, just like in standard regression.
Great, thank you. I think we have another question from Wolfgang. So there are various papers showing that some of these fancy ML methods required large sample sizes. Why do you think your results suggest otherwise?
I don't necessarily think that my results suggest otherwise. So I totally agree with this. Ultimately, we still have to do something with our data sets. Like I said, when analyzing real data with MetaForest, for example, the results seem very unstable to me. So that is perfectly congruent with the references that you're citing here. With PIMA, I have good experiences. I don't think there are papers that say that, regularized linear models are bad for small samples. I think that's a commonly accepted solution. So that's also why I'm a lot more confident about the general suitability of PIMA than for MetaForest. I think for MetaForest, you do need quite a bit of data. But the good thing is that you can check, right? You can see if the model is overfit because it will tell you that it has a negative predictive R-square. And I want to credit Wolfgang also because MetaForest uses metaphor behind the scenes. So I think I should acknowledge that.
Wonderful, great. So we have another talk from Allison who asks, great talk, very clear, thank you. For the metaphorist approach, there is moderator selection present at least 2 steps. The whole pool of potential moderators, i.e. the data that are extracted from the studies, and the small selection of moderators that go into each split when the trees are quote unquote learning. I wondered how the moderators are selected at each step.
Yeah, so I just want to, I'm going to answer this and then I want to check if I understood your question correctly, Allison. So it is true that during model building, every time one of the trees is about to make a split, it can only look at a few random moderators out of the whole data set. But the idea is not to perform moderator selection there. The idea is that there are so many trees and so many splits that every moderator gets its day in the sun at some point, right? So they're not supposed to be excluded here. It's just that unique combinations of them are examined at every split. So that is not really moderator selection. And then at the end, we perform moderator selection by looking at the variable importance and by finding out which variables have above 0 variable importance. And those are the ones that we select. And we can bootstrap that procedure to get a confidence interval for them if we want. There are also parametric methods, but I don't remember if they are compatible with Metaforest. I would have to check that. But either way, we can use a simple decision criterion to perform moderator selection and just choose all of the ones with a positive variable importance, or we can bootstrap it and perhaps we can get some kind of parametric approximation to a confidence interval, but I'm not sure. Does that answer your question?
She says that, yes, thanks. That explains selection at the learning stage. How is variable importance calculated?
Yeah, it's a good follow-up question. So variable importance is calculated as follows. First, you build the model following the procedure that I've described during my talk. Once you have the completed model, you take your original data set and pick one variable, start with the first one, and randomly shuffle it. Then you see how much the predictions that your model makes suffer in terms of prediction accuracy after that variable has been shuffled. If the predictions become much worse, then that must have been an important variable. Whereas if the predictions do not become much worse after shuffling that variable, it cannot have been a very important variable. So variable importance is defined as how much worse your model predicts the data after you've randomly shuffled that predictor, thereby losing any information that it contained. Does that make sense?
Great. And we are going to be continuing this series into 2023, and I'm actually I'd love to have suggestions about either topics that you'd love to hear about, or even speakers that you'd like to talk to. Please reach out to me or Cyprian if you have suggestions, and we would set this up for next year. So again, thank you very much, Dr. Caspar van Lissa, for a really interesting talk today. And thank you everybody for joining us. I hope you join us again next time.
Thank you for being here and thank you for having me.
Bye-bye.